version from this morning, if anyone wants to look at it. So just to talk about the general idea. So maximal green sequences originally come from cluster algebras. They're first defined by Bird and Keller. It had a combinatorial way involving quivers. And the original motivation was to give sort of explicit formulas for the refined Donaldson-Thompson variance associated with quite consensus. And these are sort of products of quantum algorithms. Thank you. Thanks. So what we're interested in today is essentially the structure of the set of all maximal green sequences of an algebra, of a finite dimensional algebra. And what one can say about this. And in particular, we'll see there's a very natural equivalence relation on this set. And then once you look at the equivalence classes, there are three partial orders, and we conjecture that these are the same. And this is somehow analogous to the fact, if you're familiar with it, that there are two partial orders on the set of tilting modules, and these have the same Hasse diagram. So just set up, I'm going to have lambda a finite dimensional algebra. There's a K, a field, and by mod lambda, I'm going to mean finite dimensional right lambda modules. So maximal green sequences were originally introduced in terms of quivers by Keller, and there's a combinatorial definition. We're working in terms of representation theory, and there are sort of three relevant ways one can define a maximal green sequence in this context. I'm going to regard these three different definitions as somehow cryptomorphic to each other. And I'm very lucky, of course, to have three mini whiteboards, so I'm going to try and do one definition per whiteboard. The first definition we're going to use uses torsion classes. These were first defined by Dixon. And for the purposes of this talk, we're just going to need the following definition. So a torsion class of lambda is a full subcategory of mod lambda closed under quotients and extensions. Important observation, these form a complete lattice under fusion. And now from this, it's quite easy to give our first definition of a maximal green sequence. So, like I said, these were originally introduced by Keller, and then this characterization is due to McGowan. A maximal green sequence is I'm going to call the complete lattice of torsion classes tors lambda. A maximal green sequence is a maximal chain in tors lambda of finite length. Okay. That's the definition of one. The second notion we're going to need, so I should say these are all equivalent, and I'll briefly say how they interact with each other. This uses silting complexes, and I might have more floor space for this. So silting complexes were originally introduced by Keller and Fossier. say the complex T in the bounded homotopic category of projective lambda modules is pre-silting. If there are no holes from T to T shifted by I for all I goes to 0. Additionally, T is silting, so it is pre-silting, if the thick subcategory generated by T is the whole of our KV approach. So the thick subcategory is the smallest subcategory which contains T displays under positive and negative shifts, cones, direct sum, and by small distance. So the smallest triangulated subcategory containing T placed under direct sum. Okay. So next we need the before I get there actually, a two-term complex. Is one has two terms. So 0 everywhere apart from giving -1 and 0. And the reason we like to study two-term silting complexes is because they categorify cluster algebras in their case. So, if you want to talk about cluster algebras, we obviously want some notion of mutation. So, a silting complex T or T prime is a left mutation of something complex T. If we have they share all but one direct sum. So I make x and y go around. So yeah, x and y decomposable. Yeah, they share all but one direct sum and no homomorphisms from just to make sure I get this right. There are going to be no homomorphisms from x to y shifted by 1. Okay. So now we can come to the second notion of maximal green sequence we're going to use for mirroring this theorem. So yeah, it's shown essentially by Demone, Yamura-Tase, then sort of the actual observation is used here for trapping that maximal green sequences of lambda are equivalent to sequences T0, T1, TR of two-term silting complexes with T naught equal to the projectives. The last one equal to the projective shifted by 1. And in the middle, we have the Ti is a left rotation of Ti minus 1. In terms of how this relates to our previous notion, it's known from work that actually you have a written that you can obtain torsion classes from these two times solving complexes. You take the two torsion classes corresponding to these, you precisely get a finite maximal. Okay. Now, all the way over here, definition number 3. So this is going to be in terms of what's called bricks. So B is a brick of lambda if the endomorphism algebra of B is a division ring. Meaning that all endomorphisms are either isomorphisms or 0. So bricks should be somehow thought of things which are somehow a bit like simple modules. In particular, you can see that they have to be decomposable. Okay, the theorem, which is due in some generality to Elisa, and then in greater generality to Lemonade, is that maximal beam sequences of lambda are equivalent to sequences B1 up to BR of bricks such that for I less than J, Hom lambda from Bj to Bi equals 0, and the sequence is maximal with this property. So it's not possible to add any more bricks to the sequence without getting some non-trivial homs in the wrong direction. In terms of how this relates to torsion classes, essentially, if you start here and take the smallest torsion class containing all of these bricks, then that's the first torsion class in the maximal chain. And then if you throw away the first one and take the smallest torsion class containing the remaining bricks, then we eventually build up a finite maximal chain of torsion classes. Okay, we're going to need a sort of interesting property that maximal beam sequences have, which are sort of best expressed in terms of this definition. This is also due to Gaussian subgenerality and Schrodingerian more generality. So for any lambda module M, there is a filtration M equals M naught contains M1 and so on to ML, which is 0, such that if I define Fi to be the ith factor of this filtration, say Mi minus 1 over Mi, then this is in filt of Bji for one of these breaks, and J1 is greater than J2 is greater than JL. So yeah, I guess that this is unique as well. So every lambda module can be uniquely built up from these breaks. And so somehow, like the way I think about this philosophically, and this sort of maybe tells you the representation theoretic significance of maximal green sequences, is that somehow it sort of provides a factorization of your module category into abelian categories which only have one simple object. So any lambda module can be built up in a unique way from these smaller abelian categories. Okay, and this is called the Harder-Narrow-Same filtration. If you know stability conditions, it's precisely the same as the Harder-Narrow-Same filtration you get in stability conditions. Okay, so we realized that board was slightly bigger. I'll go over here and introduce some notation to do with this filtration, which we're going to need. So yeah, if I let G be a maximal green sequence, and let's say we have the Harder-Narrow-Same filtration over there, I'm going to write SSF G M just for the recessive factors in the Harder-Narrow-Same filtration. So SSF stands for semi-stable factors, so I'm saying these come from stability conditions as well. So the Fi equals the semi-stable factors. For each of the Fi, I'm going to introduce this notation. So this is just going to be the multi-set of the copies of BJI, which filter Fi. So this stands for stable factors, so stability conditions language, and the stable factors of n are going to be just the multi-set union, I guess from I equals 1 to L of the stable factors of the semi-stable factors. Okay. So I guess this is all of the background. So are there any questions at this point? Okay. James, we can now state our first result. So if we let G and G prime be two maximal green sequences of lambda, then the following are equivalent. So firstly, G and G prime are related by a sequence, so I'm going to say what this means, of deformations across squares. So what does this mean? Well, if you have your post-Turing classes, say we've arrived at a Turing class Ti minus 1, and then actually also two ways to go. So your post-out locally looks like this. Then we say that two maximal green sequences are related by deformation across the square. If one goes one way around this square in the pay set, and one goes the other way around. So in this case, we have sort of finitely many squares in the pay set, and by switching the maximal chains so that we go around one side rather than the other, we eventually go from one maximal green sequence to another. Okay, so I realise there's something I forgot to say over here. So in here, if we have this mutation, so we exchange the sum and x for the sum and y, then I call, well, I'll keep it full as well. xy is the exchange pair. Of imputation. And so second condition over here is that the successive exchange pairs of G equals successive exchange pairs of G prime. Number 3. So I'm going to write this and then define it. So by S of G prime, I mean the set of indecomposable summands of Ti, where Ti is a two-term Silting complex of G. I only want one copy of to place them all. Okay. Number 4. So I guess we've seen a condition which is in terms of the process of torsion buses. We've seen how this relates to some of the data from the Silting complexes. So we see now we're going to look at how this relates to the brick side of the story of the Maurice filtrations. So for any ramp module M, the set of semi-stable factors of M with respect to G is equal to the set of semi-stable factors of M with respect to G prime. As you might guess, the last condition is that the set of stable factors with respect to each maximal green sequence are also the same. So maybe just a remark before I kind of comment on this theorem and think about what it says. That it's not sufficient to have the same set of bricks. So we know the maximal green sequence is given by a set of sequence of bricks, and obviously you can just look at the underlying set and say, well, if two maximal green sequences have the same underlying set of bricks, does that imply with these conditions? And the answer is no. And that's not, okay, maybe I'll go through the theorem a bit first. So, as is often the case for these theorems where it says the following are equivalent, some of these implications are straightforward, and there are some which are actually tricky. So showing that 1 implies anything else is relatively straightforward. So, you know, we have deformation across a square, so somehow we have a mutation of 2 times tilting complexes here, and the exchange pair there is the same as the exchange pair there. So deformation across a square doesn't change the set of exchange pairs. Because every summand occurs in an exchange pair, it's obvious that the set of exchange pairs implies the set of summands. Okay, if you think about how this relates to the Harder-Narrow-Simhan filtrations, then essentially somehow the breaks somehow come in between the inclusions of Taurian classes, and when you deform across a square, you're just sort of swapping 2 adjacent bricks. And in terms of the Harder-Narrow-Simhan filtrations, essentially what you can do is just swap the factors in the filtration, and it also gives a filtration. So we have the set of semi-stable factors is also kind of preserved by deformation across the square, and the semi-stable factors obviously imply stable factors, so it's also obvious that 4 implies 5. The difficult direction is going back in the other direction, showing that actually just having the same set of summands means that there is actually some set of squares across which you can deform to make these 2 into the same. And similarly with the filtrations, just having all of these filtration factors the same means that you can actually deform one of the other. And it's somehow not surprising somehow that just having the same set of bricks isn't enough, because you know intuitively you have order on them, and if you forget the order, you probably can't reconstruct it in a unique way up to deformations across squares. So that's maybe not surprising, but what is surprising is that actually just the set of summands does guarantee this. I haven't really had time to explain this fully, but somehow these summands, these correspond to tau rigid modules, which are in fact the sort of relative projectives of the Taurian classes. And the bricks are in fact the sort of relative simple objects of the Taurian classes. And so kind of intuitively you would expect the relative projectives and the relative simples to give the same amount of information, but actually the relative simples give less information, which is kind of a bit surprising. Okay, so this is kind of well, these conditions define an equivalence relation on the set of maximal green sequences. So this is sort of one aspect of the structure of the set of maximal green sequences of an algebra. But what's nice is that once we have these equivalence, well, once we put this equivalence relation on, we get even more structure, because we get we get 3 partial orders which are conjecture at the same. So now I'll explain that. And somehow part of the philosophy is that well, actually maybe I'll explain that after when it's time.
I have a question. So when we have this equivalence of 2 maximal green sequences in this small square, does it mean that the 2 bricks actually they are extension of the other?
When you go across the square, yeah, they have, exactly. So in terms of bricks, if you look at the sequence of bricks and you want to say, can I deform across a square by swapping the 2 bricks? The condition is precisely that they're homorthogonal and x-orthogonal.
Orthogonal and extension.
Yeah. Any other questions? So now we want to define partial orders on these equivalence classes, and kind of analogously to the situation over here, we're going to have one partial order which is somehow in terms of the process of Turing classes, one which is in terms of the tilting complexes, and one which is in terms of the breaks on the hardware applications. So I'm going to define this before stating the theorem because it's a bit wordy to define, but okay. A maximal green sequence G prime is what I call an increasing elementary polynomial definition of max green sequence G if we're in the following situation. So on the one side, we have this of the processing classes, which looks like this. Whereas on the other side, instead of just having one, we're going to have more than one. So ST, maybe I'll change the primes up here. T prime, so on to TS, where S is going to be at least one. And say, I think one of my conventions may be the opposite of what you might imagine. Say, G is going to be the one with fewer Turing classes in it, G prime is going to be the one with more Turing classes in it. So I like to think that when I say increasing, it means increasing the speed of the maximal green sequence rather than the number of Turing classes. So by extension, say that equivalence class of G is an increasing elementary polynomial definition of G prime. Okay, so now, well, now I was going to say now if I state the theorem, but really it's a conjecture. I mean, we do have some partial results. So I guess our main conjecture is that if there's G prime maximal green sequences of lambda, then following our equivalent. So firstly, that the set of the equivalence class of G is a series of increasing elementary triangle definitions of the equivalence class of G prime. Secondly, that the set of summands of G is included in the set of summands of G prime. So yeah, this kind of order is particularly easy to state. The last order, which uses quite Maurice filtrations, is kind of a bit more subtle to state. The rough idea is that when we go from G prime to G here, we're sort of replacing more breaks with fewer breaks. So somehow our hydrodynamic filtration should get finer as we go from G prime to G. And obviously that's sort of like straightforward notion of refinement is filtration, but you just add submodules. But that doesn't work here because we have an equivalence relation, so actually the set of submodules in the filtration is not respected by the equivalence class, because you'll be changing them when you take the equivalence maximum green sequence. So anyway, so here's the definition. It's that if we take a lambda module M and we want to look at its stable factors with respect to G, then somehow if we want to do that, because G, the filtration from G should somehow be a refinement of the filtration from G dash, we should somehow be able to do the one from G dash first, and then do the one from G. So, i.e., if we look at all of the bricks, which are stable factors of M with respect to G prime, and then we look at their stable factors with respect to G, then it should just be the same as looking at the stable factors of M with respect to G. Okay, so almost out of time. So I guess I should say partial results we have in general that one applies to, that's actually pretty easy. So we can also show one implies three, which is a bit harder, but still not too harder. What is quite hard to show, so we can actually show this conjecture in general for a particular class of algebras, namely Nakayama algebras. So if you're not familiar with Nakayama algebras, the algebras such that all composable modules are used serial, meaning they have a unique composition theories. I guess I'm not finished. I say again. So when I saw Gordana in Toronto late last year, she gave us all about Nakayama algebras, and she was saying that even something like Nakayama algebras, which you know really well, you can still find new results. So it's a shame she's not here to see this talk, but yeah, there's another new thing about Nakayama algebras, and yeah, I think I'll finish that.
Any questions from the audience?
Yeah, sure. So somehow the hardest implication is 3 to 1, and roughly how it goes is as follows: you sort of do it inductively on the length of the sequence, which after the point where they diverge. So if you're going down the chain of order classes, at some point they split off, and you essentially want to make that as late as possible. And so you look at the point where they diverge, you have two particular summands in the exchange pair there. You know, because the summands are equal, that those summands actually appear later somewhere in the maximal green sequence. So you essentially look at where they appear later, and then you try to move them backwards by deforming across the square. If you find that actually you can't, there's a point where you can't move it backwards, then you must have some summand which occurs, but then essentially, because then you know that summand occurs in the other maximal green sequence after the exchange pair, you get a combination. That's essentially how that works. In terms of the filtrations, well, yeah, so the criterion for swapping bricks is that we showed is that they're homorthogonal and x-orthogonal, which I think is a bit hard to show anyway, I think. And essentially, if there comes a point where you can't swap them, it essentially it has to be because they're not X orthogonal, because somehow you know the bricks occur in different orders, and you have the homorthogonality condition by definition. You know they actually are orthogonal. So if you can't swap them, it must be because they're X orthogonal, not X orthogonal. So then if you look at the middle term of the short exact sequence, you show that that actually has different filtration. So yeah, that's right, I guess.
Is it easy to give an example showing that if you just have the same bricks appearing, that doesn't give you equivalent maximal green sequences?
It's maybe a little too long to write down in total now. I mean, I could depending on how well people want to say it, I could go into the algebra is just non-linearly oriented so it's not massive, but yeah, if you compute the base sets of two-type sorting complexes and the Gaussian classes, then you can find two which have the same bricks but different summands. And it's kind of like philosophically the reason is because like if you look at this module, it's not, well, this brick is not uniserial, and it has somehow two different possible filtrations, and in each maximal green sequence you'll have each of these 3, 1, 1, 2, 3, 2. I mean, not in this order. But they'll be ordered in one maximal green sequence in such a way that this is the validation filtration, and in the other maximal green sequence in a way such that that is the validation filtration. And yeah, by the theorem, they have to have different summands.
From the line.
Okay, there's a question on the back. I think.
Yeah, so how do these maximal green sequences, how are they used to compute DT invariance?
Right. Well, so it kind of depends a bit what you mean by DT invariance. So there's a thing called the refined DT invariant associated with the quiver, which is somehow the generating series for the motives of the modularized spaces of representations of particular dimension vectors. If you want to compute that generating series, then, well, essentially because of the Auslander property, you can factorize it just into the generating series for these categories of bricks, which you can say very easily. That's basically the answer.
Maybe a comment. If I understand correctly, so the DT invariant here, if you take the conservation of non-commuted version, so it is a composition product of the quantitative algorithm of all the diagonals.
Right, yeah.
There is a maximum green sequence, and the power of each quantitative algorithm is the positive the usual. So in general, if it is not necessary to mutation, you might get a negative power of.
Right.
Here.
Right. Yeah, that's also true. So yeah, these quantitative algorithms are precisely these generating series for the representations.
Are there more questions? No, that's